Let's talk about loudness and localization now. Like pitch, which is the perception of frequency, where frequency is the physical phenomenon, loudness is the perception of intensity or amplitude of sound. And so loudness is strongly related to amplitude. This relationship is approximately logarithmic, which means equal ratios of amplitude are more or less perceived as equal increments of loudness. We are very sensitive to small ratios of frequency, but we are not very sensitive to small ratios of amplitude. In fact, if you want to double the perception of loudness, you need about a tenfold increase in intensity. We are sensitive to about 1 decibel of amplitude ratio, and our sensitivity to loudness is frequency dependent, which we'll talk about shortly. What I would like to do now is illustrate this logarithmic relationship by first playing some linearly increasing amplitudes. If you listen to that carefully, you will find that the initial steps in amplitude seem to be larger steps than the final steps in amplitude, even though those are equal steps in linear terms. Now what we'll do is play the same sequence, but we will increase amplitudes exponentially, which means the same ratio from each step to the next. And so with more or less equal ratios of amplitude, we hear more or less equal increases in loudness. And the final thing I'd like to play is a 2 dB change in amplitude, just so you can hear what that sounds like. That's very close to the limit of our ability to detect amplitude change. You may have felt like there was an amplitude change, but maybe not so sure whether it was louder or softer. So one thing that this tells us in computer music synthesis is that if you want to make something louder, don't increase by 10% or 20%. You might start actually by doubling the amplitude to make sure that you can hear it, and then you can dial it back, or if that's not enough, you can increase more. Now, I mentioned the Fletcher-Munson curve. This is a very famous curve. It's actually been replaced by a new curve that's an ISO standard, which is shown here colored in red. The original Fletcher-Munson curve is colored in blue here. And what these curves show are the amplitudes at different frequencies that give rise to the same perception of loudness. And you notice that these curves are not flat. And what that means is that the fact that these curves decrease starting at low frequencies on the left and decreasing as we move to the right, that means we are becoming more sensitive at these higher or these mid-range frequencies. So around 1,000 to 4 kilohertz, we become most sensitive to sound and most able to detect the quietest sounds. And then as we move to higher frequencies, over on the right, we become less sensitive once again. So this is quite interesting. This means that if you sweep a sinusoid from low frequency to high frequency at equal amplitude, you will hear that the sound appears to get louder for a while until you hit around 4 kilohertz, and then the sound will begin to get quieter, and depending on how loud it is, you will stop hearing it at some point before you reach 20 kilohertz, even if you can hear loud sounds at 20 kilohertz. Let's talk about localization now. Localization is the ability to perceive the direction of a source of a sound and perhaps the distance of that sound. And we have multiple cues for localization, including amplitude, phase, or timing, and spectral effects. So starting with amplitude, if we hear something louder in our right ear than our left ear, then we will perceive that the sound must be coming from the right, all other things being equal. The phase or timing cues means that if we hear a sound arriving earlier at our right ear than our left ear, then we will calculate that the sound must be coming from the right in order for the sound to reach the right ear first. And we are very sensitive to that. There are also spectral effects. So what happens is the pinna, which are our outer ears, are, as you know, non-uniform. And there's a reason for that. At least part of the reason is that our frequency response of our ears differs depending on the direction from which the sound is coming, because sound reflects off of the pinna, which are very irregularly shaped, and these reflections depend on the direction the sound is coming from. And these reflections either enhance or partially cancel different frequencies in different ways. And so the combination of the pinna and our amazing brains is able to compute something about localization, especially in cases where we're talking about elevation. How high is the sound? Because obviously, if the sound is directly in front of us, then the same amplitude should hit both ears. The timing delay does not change as we go up and down because the ears are left and right. And so the only thing left is spectral effects. And yet we do have a sense when a sound is overhead or versus in front of us. So all of these effects, amplitude, phase, and spectral effects, can be described really as filters or characteristics of filters. And so sometimes we lump all of these effects together and call them the head-related transfer function. A transfer function is just the change in the spectrum from source to destination. So we're expressing the entire broadcast channel, if you will, as some kind of filter. And so that filter is the head-related transfer function. It's also called HRTF, and so you may have seen artificial localization systems for video games and for virtual reality applications based on HRTFs. And we'll talk about these more later in the course. Environmental cues are also important for localization. If sound is reflected off of walls, then it gives you a sense of where you are, how far away the walls are, and perhaps a little bit about the location of the sound. Also, the reverberation and the ratio of reverberation to direct sound is important for distance estimation. And especially in computer music, if you want to create the effect of a sound source fading off into the distance, the way to do that is not to simply turn down the amplitude of the sound, but instead you should vary the ratio of the direct or the dry sound to reverberant sound. Finally, the knowledge of the sound source is very important. One of my favorite illustrations of this is that if you put someone in a room and you put on headphones and you have them listen to stimuli and ask them where the sound is coming from, you'll get some answer. And if you do this same experiment, but you put a loudspeaker in front of them, or maybe up high, who knows, and even if the loudspeaker is not connected, it's not making any sound, everything's coming from the headphone, the visual cue of that loudspeaker will change the responses that you get from subjects. Let's talk some more about acoustics. First of all, the speed of sound is about 1 foot per millisecond. I know that's very unscientific. I'm not using meters per second. And I'm not giving you a very precise number, I'm just saying about. But in fact, sound travels at different speeds, at different altitudes, at different barometric pressures, at different temperature, different humidity. Those all affect the speed of sound. So there's no precise number in the sense that the speed of light is exactly some number. The other thing about the speed of sound is compared to the speed of light, which we in everyday terms think of as just instantaneous, sound actually does take time to travel. It's 1 foot per millisecond. So for example, if you stand back from a wall and clap, then you can hear the reflection of that clap. So you can actually perceive the time it takes for the clap to go to the wall and come back. And speaking of reflections, in most listening environments, we get not just one reflection, which if we can hear it is called an echo. In most environments, we hear many, many reflections, and sound bounces around, and it gets so complex that what we hear we call reverberation. It's the diffuse superposition of millions and millions of echoes. In addition to reflection, sound refracts. This picture over on the right of the ocean is illustrating refraction of ocean waves around a rocky shore. You can see waves coming in one direction, but then if you look, you can see a wave, some waves crashing on the shore going in a completely different direction. And that's an example of refraction. You may have learned about the refraction of light or seen the refraction of light that creates rainbows. In light terms, the change of frequency from the lowest frequency of light to the highest frequency of light that we can see is a ratio of about 2 to 1, or we could say that's an octave. With sound, we hear from 20 hertz up to maybe 20 kilohertz. So that's 3 orders of magnitude. That's a huge change. It's more like 10 octaves. So that means that when you're listening to sound, some of the sound waves that you hear could be 50 feet long, and other sound waves will be just a fraction of an inch. And so these 50-foot long sound waves will go right through you or around you. They'll go around objects of fairly large size, whereas the short, tiny wavelengths will bounce off of you. They bounce off of your pinna. They can be masked by a person sitting in front of you, and so you get a very different dispersion of sound depending on wavelength. Now I'd like to talk about a very important concept, which is linearity. Linearity means that a system, and let's just think about transmission of sound. So we'll think about what happens from the source of a sound to the listener of the sound, and we'll call that whole process the function f here in these equations. So what linearity means is that if I increase the sound at the source, I will get an equal increase at the listening side of the channel of f. So that's f of ax equals a times f of x, if f is linear. The other property is sometimes called superposition. If I have 2 sources, x and y, and I play them at the same time, then linearity says that the effect will be at the listening end will be the effect of the input x plus the effect of the input y. So why does that matter? Well, first of all, airs, rooms, performance spaces are all very linear, and many of the processes that we use on sound, such as filters, are designed to be linear. And so linearity means that if there are 2 people playing at the same time, or 2 sound sources, then the signal at the listening end is equivalent to what you would get from one of those sounds plus what you would get from the other sound. And so, for example, that means if we want to play two oscillators that we synthesize, the way that you combine them and mix them together is to just form a weighted sum. The other interesting thing about linearity is that you know that we can break sounds, decompose sounds into sinusoidal components, right? That's the Fourier transform. We can break a sound up into different frequencies. So if we have a linear system and we know what the system does to each one of those frequencies, then by superposition principle, we know what the system does to any sound because we can break it up into those frequencies, compute the transfer function at each of those frequencies, and then sum those transfer functions together. So that is a way of looking at what a filter does. A filter associates a different scale factor with each frequency. And the cool thing is that because filters are linear, if I add two sounds and put them through a filter, that's equivalent to putting the first sound through the filter, put the second sound through the filter, and then sum the results, because it's all just forming weighted sums. And again, that's called the superposition principle. To summarize some of the things we've been talking about, we have some percepts. We perceive pitch, we perceive loudness, we perceive timbre, and there are physical phenomena that are associated with each of these percepts. Pitch is associated with physical frequency, loudness is associated with the physical intensity or amplitude, and timbre is associated with the physical spectrum. Our perception of pitch and loudness is roughly logarithmic. Perception is a very complicated thing, though, so it's not that we're actually somehow accurately measuring frequency or intensity and applying an accurate log function, and that's the percept. No, so that this logarithmic relationship is just approximate. And we saw that approximation, for example, in the Fletcher-Munson curve that says, well, our response at different frequencies or our perception of the same amplitude at different frequencies is not really uniform and flat, but it's frequency dependent. Okay, struck objects typically exhibit characteristic frequencies. Remember these modes of vibration, and you saw that in the guitar top two modes of the guitar. And so if you tap on a guitar, different modes are going to vibrate. Each mode has a characteristic frequency, and each mode typically has an exponential decay rate. On the other hand, driven oscillators typically exhibit almost exactly periodic signals, and hence they generate harmonic spectra. That's something that we're very sensitive to, probably because anytime we hear a sound with harmonic spectra, we know it's driven, and so therefore we know that there's an energy behind it and it might be alive. Finally, we talked about the speed of sound, transmission of sound, and the superposition principle that applies very accurately to sounds in our everyday world because of linearity.